Okay, here's a solution to homework set number 3 for ECE 321 analog electronics. The first problem is given a transfer function, find the differential equation that relates x and y. And this is a way to write a differential equation that's a little bit easier. To do that, what I can do is cross multiply out the polynomial. Sy means the derivative of y. So s squared y is the second derivative, where prime means derivative, y doubled prime is second derivative. Sy means the first derivative, and y just means y. So that's the differential equation that corresponds to that transfer function. Anytime you see transfer function in S, think differential equation. Part B, find y given the input is a DC term and an AC term. To do that, use superposition. At DC, S equals 0. This is the gain everywhere. The assumption is everything's e to the st. So if s equals 0, I have e to the 0 t or 1. That's a constant. This is the gain everywhere. At DC, the gain is 60 over 30. Gain is 2. Here's my input. Output is 4. So that's my DC term. For the sine wave, the AC part right over here, this is the gain everywhere. All I care about is what's the gain at 5 radians per second. So analyze at s equals j5. My input is 3 minus j4. Real part is cosine, minus j is sine. That's the standard in phasor notation. Multiply it out, I get a complex number. And what that means is real part's cosine, minus j is sine. Put the two together, I have my DC term and my AC term. That's my total answer, DC plus AC. Problem 2. Design a circuit to implement this transfer function. Well, this has real poles, so what I can do is just use a two-stage RC circuit, have R go up by 10 times for each stage to reduce loading. And the first stage, 1 over RC is 3. Second stage, 1 over RC is 10. Pick R, solve for C. The DC gain, plug in S equals 0. This has a DC gain of 2. So this will just have a DC gain of 1. I need to add a circuit with a gain of 2, and that's this guy right here. DC gain is 2. So this is a way to implement that filter. Problem 3 is design a circuit to implement a filter with complex poles. And it's a slightly different circuit. That's this guy right here. 1 over RC is the amplitude of your poles. Here the poles have an amplitude of 5.48. So pick R, solve for C, 100K, 1.8 microfarads. Instead of going to ground, I have positive feedback. That gives you the complex poles. And the angle is set by this, K. K is 1 plus the ratio, is 1.452. 3 minus K is 2 times the cosine of the angle. And the angle's at 74 degrees. Solve for K, I get 2.54. That's 1 plus the ratio. So this is 1.45 to 1 ratio. 100K, 145K. And that'll implement this filter. Again, slightly different circuit. Real poles will just be RC circuit. Complex poles will be this one. Filter design using fmin search. Come up with a circuit or a filter to approximate this ideal filter. And what that looks like is should begin at 1 at 2 radians per second, and then goes to 0 at 4 radians per second. That's what I want. To do that, I can let fmin search solve for you. So what I'm going to do is I'm going to guess the parameters a, b, c, d, e. So I'm going to create a function called costf, passing the matrix z. To interpret z, I'll parse it like this. Z is a 5x1 vector. That means a, b, c, d, e. My ideal filter has a gain of 1 for frequencies less than 2. It's this guy right here is 2 minus 0.5 omega for frequencies between 2 and 4. The actual g of s is a function of a, b, c, d, e. Take the difference in the two filters, return the sum squared error, and plot it just for fun. And here's what I get. So for example, if I guess a, b, c, d, e is 1, 2, 3, 4, 5, I get the red line. The blue line is what it's supposed to be. Take the sum squared error, I get 88. To optimize the filter, I want to minimize this number, or make these two as close as possible. So if I run fn search saying I want to minimize this function, here's my initial guess, go. About 20 seconds later, it comes back saying, here's the best I could do. And here's the corresponding graph. Again, not bad. fn search actually does a really good job designing filters. What A, B, C, D, E means is here's your A times C times E. Here's your A, B, C, D, E. That's the filter that has the red line. And the blue line is what I want. So that's one way to design filters. Let fn search design it for you. Problems 4 through 8 is take the previous homework set and now add a filter in the middle. Kind of your pick what you want to do. I chose a low pass filter, meaning I want to pass frequencies below 0 and 250 Hertz. So here's at 250. I want the gain to be somewhere between 0.9 and 1.1. At 500 Hertz, I want the gain to be less than 0.2. Any filter that does that is okay. So come up with a filter that does something kind of like this, then the gain drops off and does that. The first step is to find out how many poles you need. As the frequency doubles, the gain drops down to 0.2. Solving for n, I need 2.32 poles. Let's round up and make it third order. I like Chebyshev filters, so this is from the lecture notes, a Chebyshev filter with a corner at 1 radian per second. Let's put the corner at 238 Hertz, just as a wild guess. Or 1500 radians per second, that's where that number comes from. If I plot the gain versus frequency, here's frequency, omega is 2 pi f, s is j omega. Here's my poles. For a Chebyshev filter, here's my filter. And plot gain versus frequency, and also put a red X at my 2 points. Gain needs to be at least 0.9 at 250, 0.2 at 500. Here's what I get. So at 250, the gain's good. At 500, the gain's good. That's a good filter. And sometimes you have to guess again. Change the amplitude of the poles, and basically change these two numbers. What should the corner be to meet these specs? To build that filter, do it in 3 stages. Okay, 2 stages. The first is a real pole. Real pole is at 1275. Pick R, solve for C, and C is 78 nanofarads. The second stage, pick R, solve for C. Third stage, I want the angle to be 69 degrees, so 3 minus k is 2 cosine of the angle. I get 2.3. And to test it, I can take this, simulate in Circuit Lab, sweep the frequency V1, measure V2, and here's what I get. That seems to meet the requirements. And validation. Build it. So here's a circuit from week 1. That's my 2.5 volt source, my amplifier times 4. Here's the push-pull amplifier. It's really just a push amplifier. Here's my filter. So that's my third order Chebyshev low-pass filter, I think. It's supposed to be. So here's testing out the filter. Here I've got a sine wave coming in. And this is going directly from the first stage to the push-pull. Running through the filter, it's blocking 800 Hertz, going down to 400, 200, 100, and at 100 Hertz, this is the output of the filter, input of the filter, basically the same, a little bit louder because the filter adds a little bit of gain at DC. At the corner, it's 250 Hertz with a filter, without a filter, and 500 Hertz. After the filter, without the filter, with a filter, without a filter. If we put that on a voltmeter, you can actually get some numbers. And the more fun part is, let's turn that off, play music through it. And this is without a filter. With a filter. And with a filter. Without. With a filter. Okay, so that's homework set number 3 for ECE 321. Apply a sine wave in, measure the gain at a couple points. Like here, I would measure the gain at maybe 100, 200, 400, 800. See if those gains match up on the graph. That kind of verifies that your circuit is working correctly. Then to demo, the fun part would be apply say music in to see what it sounds like. So that's homework set number 3 for ECE 321 Analog Electronics.